Okay, I want to do one more thing here before we leave off of heat exchangers and move on to radiation. And that's talk about some of the characteristics of how these effectiveness NTU solutions behave and why they behave the way they do. So these are the solutions, right? There's a bunch of equations. It's really tempting just to use them kind of blindly in the same way that you can use convection correlations blindly without ever thinking about why they're doing what they're doing. It's almost always a bad idea. So let's look at how these things actually look and why they look the way they do. So if I were to plot effectiveness, so let's take this one here. Effectiveness is a function of NTU for different capacitance ratios. I can reflect this entire solution in one graph. So I'm going to do that for a counterflow. I'm going to do that for a parallel flow. If you think about it, these are about as far apart as they can be in terms of the flow direction. And then I'll pick one of these cross-flow correlations as well, one of these mixed, unmixed versions. So that's what I've done here. So here I have a counterflow. So here's effectiveness as a function of NTU. And every blue line represents a different capacitance ratio. Over here I have a parallel flow heat exchanger. So effectiveness is a function of NTU, and again, different capacitance ratios. And then down here, counterflow, cross flow. So I'm sorry, this must be actually unmixed cross flow. So effectiveness NTU, and then different capacitance ratios. So these different capacitance ratios go from completely balanced capacitance ratio of 1 to completely unbalanced, right? This capacitance ratio of 0, and it's the same for all of these. So this is a lot of information to look at all at once, but there are a couple of regions where these different configurations behave exactly the same. And one of those regions is in the place where the capacitance ratio goes to 0. So if I have a heat exchanger that is completely unbalanced, so this capacitance ratio equals 0 line, it's going to behave the same whether it's a counterflow or a parallel flow or a cross flow or a shell and tube. It doesn't matter what the configuration is. The effectiveness as a function of NTU for a counterflow heat exchanger, this top line with capacitance ratio equals 0, is exactly the same as it is for a parallel flow heat exchanger or this cross-flow heat exchanger. In other words, these upper blue lines are identical to one another. So that's kind of interesting, and we should ask ourselves maybe why that is the case. What is it about that operating limit that makes all of these configurations look the same? And to do that, we should maybe look inside and see what the temperature distribution is doing in the situation where the capacitance ratio is going to 0. So if the capacitance ratio is going to 0, physically what that means is that one of the fluids is changing temperature, and then the other fluid is not changing temperature much at all, right? The capacitance ratio, the fluid with the capacitance ratio that's really large is not changing temperature very much. So if I look inside of that heat exchanger, what's going to happen is one of these fluids is going to change temperatures and the other really isn't at all. So here's the parallel flow configuration. I've decided that the cold fluid has an infinite capacitance ratio, right? It's got just a large mass flow rate, or maybe it's evaporating, whatever. The cold fluid temperature doesn't change much as it goes to the heat exchanger. It's warming up, but not very much at all. On the other hand, the hot fluid temperature does change because it has a finite capacitance ratio. So this is what it looks like in parallel flow, right? I come in on the left, the cold fluid warms up a tiny bit, the hot fluid drops a substantial amount. If I go over here and look at the counterflow heat exchanger in the same limit, well, the cold fluid comes in at the left, it warms up a tiny bit. The hot fluid comes in on the right and it drops a substantial amount. But actually, these two heat exchangers, they're identical in terms of what the temperature difference is doing as a function of position, right? I mean, they flipped the axis, but they're the same temperature difference as a function of position. And it wouldn't matter if I do the same thing on a cross flow or a shell and tube heat exchanger, right? As the fluid flows through the heat exchanger, the temperature of one of the fluids doesn't change at all, and therefore the orientation of the two flows doesn't matter at all, right? That's what's coming. And actually, this limit, the limit of the capacitance ratio goes to 0, the effectiveness is a very simple function only of the NTU. It's 1 minus the exponential of minus NTU. This equation, by the way, is exactly what you get for your internal flow problem when you have a set temperature boundary condition, because that's exactly what this is, right? This is a set temperature boundary condition. So if you go back and look at that internal flow lecture on energy balances, and you look at the energy balance that has to do with the case where the temperature of the pipe wall is set, you can turn that solution into this solution here, because it's an identical situation, right? It's a heat exchanger where one fluid is experiencing a thermal interaction with a constant temperature sink. So that's why that's the case. The other case, let's go back and look at this. The other case where configuration doesn't matter is actually down here when NTU becomes really small. So if NTU is, let's say, less than about 0.4 or so, all of these lines down here at the small NTU region are exactly the same. These all collapse to the same line, and configuration doesn't matter again. So let's think about why that's the case. And basically what's happening there is your heat exchanger is just not very good, in the sense that you're not transferring enough energy for either of your two fluids to change temperature very much at all, right? So if I look inside of a parallel flow heat exchanger, what I'm going to see is that, yeah, the hot fluid and the cold fluid come in on the same side. The cold fluid increases in temperature a little bit. The hot fluid decreases in temperature a little bit, but neither change temperature very much, right? And so throughout the entire heat exchanger, I basically have a constant hot fluid temperature interacting with the constant cold fluid temperature. If I switch the configuration to 180 degrees, so now the cold fluid comes in on the left, the hot fluid comes in on the right in a counterflow situation, it doesn't really matter, because again, the hot fluid doesn't change even though it's flowing in the opposite direction. Its temperature doesn't change much, and the cold fluid temperature doesn't change much. So you basically have the same temperature difference existing inside the entire heat exchanger, right? And in that limit, that's kind of the one time you're allowed to say that the rate of heat transfer is approximately equal to the conductance, so 1 over the total thermal resistance times THN minus TCN, right? This is the one time where that temperature difference, THN minus TCN, actually exists pretty much throughout the entire heat exchanger, right? And that's because the temperature of the hot fluid comes in at THN, it just doesn't change much. The temperature of the cold fluid comes in at TCN, and it just doesn't change much. So this is my Q dot approximately. If I substitute this Q dot into my definition of effectiveness, I get this. If I cancel out THN minus TCN from the top and the bottom, I see that in the limit that NTU goes to 0, I just get UA over C dot min. I get that the effectiveness is approximately equal to NTU. So if I go back and look at these again, down here, this line that all of these solutions collapse to is basically effectiveness equals NTU, right? So you can sort of see that here. When NTU is about 0.2 right here, the effectiveness is about 0.2, right? 0.1, 0.1. There's a line with a slope of 1 that these all collapse to. As NTU gets bigger, these all diverge, right? And that's because, well, I don't get this limiting behavior anymore, right? The temperatures are actually changing quite a lot when NTU gets bigger and bigger. All right, so two regions where configuration doesn't matter. One is the capacitance ratio is up here at 0, and the other is if you're down here at low NTU. Now, if you're at a capacitance ratio that's above 0, so you're going more towards a balanced heat exchanger, right? You're getting closer to 1, and the NTU is not really small, so maybe you're up here at 1, 2, 3, 4, you're out here. In this region, you can see there's actually kind of a substantial difference between how these different heat exchangers behave, right? If I look particularly at how a counterflow heat exchanger behaves versus how a parallel flow heat exchanger behaves out here, very, very different, right? I mean, let's go to an NTU of 4 and a capacitance ratio of 1. So at an NTU of 4 and a capacitance ratio of 1, my counterflow heat exchanger can be 80% effective. My parallel flow heat exchanger can only be 50% effective. That's a very different performance under the same conditions, right? So why is that the case? So let's think about that. So here is a counterflow heat exchanger, and then right next to it I have sketched up a parallel flow heat exchanger, right? And we're going to look at this in the situation where the capacitance ratio is equal to 1. So I'm at a point where the capacitance ratio is equal to 1, right? And so I'm away from that very unbalanced limit. Configuration should matter. And we're also going to look at a case where the NTU is not really low, right? Which means that I'm actually getting some pretty substantial temperature changes in my fluid. So what does the parallel flow temperature distribution look like in that limit? Well, for one thing, I know that however much the cold temperature rises, that's how much the hot temperature should drop. So that's shown. The other thing I know is that the cold temperature rise and the hot temperature drop should be pretty substantial, right? So that's also reflected here. If I go over here and do the same thing for the counterflow heat exchanger, I'm sorry, this is a parallel flow heat exchanger. Let's go for the counterflow heat exchanger. Same idea, but now the flows are in the opposite direction, right? So here I come in at TH in, my hot fluid drops. I come in here at TC in, my cold fluid rises, right? They both rise and drop the same amount. The temperature changes are the same, and the temperature changes are substantial. But this temperature distribution and this temperature distribution look very, very different from one another, right? In fact, if you think about continuing to increase the NTU, making it bigger and bigger and bigger, what's going to happen? Well, over here for this parallel flow heat exchanger, what's going to happen is these two temperatures are going to get closer and closer and closer, and eventually they're going to meet. They can never cross, right? You can never transfer energy from cold to hot, so you can never cross, but they can eventually meet, and that's what they do. In this case, you can see they have to meet out here at the exit, and eventually they'll come together, and they just can't get any better than that, right? No matter what you do, you can't do any better than forcing these two temperatures together at what's called the pinch point. This is the pinch point for that heat exchanger, right? And it limits the performance, right? If you think about this parallel flow heat exchanger with a capacitance ratio of 1, the best I can ever do is to take this cold inlet temperature and get it to halfway to the hot inlet temperature, or take this hot inlet temperature and cool it down to halfway to the cold inlet temperature. That's an effectiveness of 0.5. Right? No matter how big I make this heat exchanger, my parallel flow heat exchanger configuration can only get to 0.5 if the capacitance ratio is 1. And in fact, if you go back and look at this, my capacitance ratio is 1 here. I can never get better than 0.5, right? On the other hand, my counterflow heat exchanger doesn't suffer from that limitation, right? Again, if I make the heat exchanger better and better and better, these two streams will approach each other. But in this case, they're going to approach each other everywhere. The pinch point is, all the way along here. So I can actually still get the cold outlet temperature up to the hot inlet temperature. Still get the hot outlet temperature down to the cold inlet temperature. I can still approach an effectiveness of 1 in this counterflow heat exchanger, right? You can tell it's going to take a long time because this temperature difference is getting really, really small. But if I go back and look at this, if I'm over here in my counterflow heat exchanger, I have a capacitance ratio of 1. I'm not asymptoting at any number other than effectiveness of 1. It's taking a long time to get there. But if I make NTU big enough, I can actually approach 1 for this counterflow heat exchanger. So there's a fundamental limit associated with a parallel flow heat exchanger and how large the effectiveness can get. And that's given by this equation here. As the NTU approaches infinity, the effectiveness of a parallel flow heat exchanger depends on the capacitance ratio. If the capacitance ratio is 1, we already said the effectiveness has to be 0.5. If the capacitance ratio is larger than 1, then the effectiveness can be larger because it's not limited in such a way. And just to be clear, these are the two extremes, right? This guy here is always going to give you, this parallel flow heat exchanger is always going to give you the worst possible performance. The counterflow heat exchanger is always going to give you the best possible performance. Every other configuration we talked about is going to come in somewhere between these two limits, right? So if we look at a capacitance ratio equal to 1, and then the number of transfer units on the x-axis and plot effectiveness, here's our parallel flow heat exchanger. It's this bottom line. it limits to 0.5. You can't get any better than 0.5. Here's our counterflow heat exchanger. It's this top line, right? It's going to eventually approach 1, but it's going to take a long time. Here's every other configuration, right? Crossflow, shell and tube. This is a different crossflow where only one fluid is mixed, but you can see they all come in somewhere between counterflow and parallel flow. The ones that are most like a counterflow will be up here, and the ones that are most like a parallel flow will be down here, but they're going to come in between. As we make the capacitance ratio smaller, this spread of these different configurations gets smaller, right? So if we go from 1 to 0.5, we still have the same ranking going from counterflow all the way to parallel flow, but the spread here gets smaller. And then if we go all the way to 0.25, the spread gets even smaller. If I go to 0, it'd be a single line again, right? So that's kind of how these things behave. So one last thing to talk about just briefly is heat exchanger design, right? So, heat exchangers, I think I said this before, become sort of the heart of most thermal fluid systems, and their design really is central to the design of the system itself. You're usually, when you say I'm going to go design an air conditioner or something like that, you're really talking about designing a heat exchanger that does the best job for the rest of the system to give you the best performance. And that design process is always going to be some kind of a trade-off, right? Whenever you design a system, you're always basically trying to optimize dollars, right? You're trying to spend the smallest amount of money to do some kind of job, right? So if you look at all these heat exchanger curves, they might be a little different, but they all have very similar behavior in that they initially take off pretty quickly. The effectiveness goes up really quickly with NTU, but right around an NTU of 2 or 3, they're going to bend over and eventually stop changing very much at all, right? And that sort of tells you where the sweet spot is. If you think about designing a system, you're always going to be trying to minimize total cost. And total cost is going to be the sum of some kind of a capital cost, which is how much I had to pay for my heat exchanger, and an operating cost, which is how much I have to pay to operate my system. So how does capital cost behave as a function of NTU? Well, if I have a non-existent heat exchanger, it doesn't cost anything. And then, as I make my heat exchanger bigger and bigger and bigger, the capital cost is going to increase, maybe linearly, maybe less than linearly. There's entire books that tell you sort of how to scale dollars with size of heat exchanger, but certainly it's going to go up monotonically and continuously, right? It's never going to stop going up. You don't get to a point where you get free heat exchanger. So that's this blue line. If you think about operating cost, if I have a heat exchanger that's not very big and not very effective, I would expect my operating cost to be quite high, right? I have to buy a lot of energy, or my plant isn't very efficient or something like that. And so my operating cost is really pretty bad. And then as I add a larger and larger heat exchanger, my operating cost is going to come down, and eventually it's going to flatten out, because eventually I get across the knee of this curve, and buying more heat exchanger is actually not making my plant more effective. It's not increasing the effectiveness. And so this is going to come down for a while, but then it's going to stop changing. So if I add the red line to the blue line, I get what I really care about, which is the total cost. And you can see, there's going to be a minimum in the total cost, right? There always is. There's a minimum where, you've sort of hit that knee, and buying any more heat exchangers continues to cost you money, but doesn't really bring any benefits, right? And so now you're climbing up the other side. And if you look at where this minimum occurs, it's almost always right around an NTU of 2 or 3. And the reason is because that's exactly where this red line starts to bend over and doesn't really drop anymore, right? So, one of the ways that you should sanity check a design of a heat exchanger is calculate the NTU, right? Just look at where you're at on this curve. If you've decided you need a heat exchanger where the NTU is 20, maybe that's true, right? But you ought to at least ask yourself why. Why do I want to be way out here, right, where my operating cost is not changing very much at all, but my capital cost is continuing to go up, right? That would be a situation where maybe energy is incredibly efficient, or your heat exchanger is just basically free, right? Something like that is pushing you out into that region. Or alternatively, if you're way down here with an NTU of 0.1, that would bear thinking about too, right? I mean, maybe energy is just so cheap that you don't care, or maybe your heat exchanger is so expensive that you can't buy much of it. But you ought to, at least in your mind, be able to explain that to somebody, why you're in this kind of weird condition. And what you'll find most of the time is you're not in a weird condition. You're right here in this sweet spot, and the sweet spot is an NTU that's pretty reasonable, right, in the 2 or 3 regime. All right, so that's kind of it for heat exchangers. It's certainly more than enough for you to do your homework. What we'll do moving forward into the end of the semester is radiation. So we'll start that in the next lecture.